We can do coolants. Requirements of a coolant: it must prevent cavitation, corrosion. It must lubricate moving parts in the system. It must be compatible with all seal materials, polymers, pipes, hoses, everything. It's mixed with water. It will raise the boiling point of water. It will lower the freezing point of water. And then many different types of coolants available. When I say types, trade names. And many of those are not compatible with each other. Okay, looking at trends in engine design. I mean, these will work in any sort of system, not only in engines. If you've got a heat transfer system in a building that needs a coolant or heat transfer, some additive in the water to stop corrosion, you can use these coolant additives. But in engines, there is a move to smaller, higher efficiency engines. So there's less coolant flow in the engine, and the coolant has to do more work. And also because of that, the operating temperature is getting higher in engines. It can be over 100 degrees. And to prevent the water from boiling in the cooling system, the system is pressurized. It's also moved to lighter materials, a lot of aluminium used in engines, and even plastic parts in engines. Amazed, I was looking at a Mercedes engine, latest Mercedes engine, how much plastic there is inside the engine. Okay, just looking at overall temperatures inside the engine. This is a turbocharged engine. In the combustion chamber, here you've got a temperature of up to 2,000 degrees C in the combustion chamber there. So the exhaust is coming out at 600 to 800 degrees C. The cylinder liners up to about 120 degrees C. The cylinder head up to 250 degrees C. And just the gas at the end of the compression stroke before combustion starts, 450 degrees C. So there's a lot of temperature in the engine. And the coolant is circulating all the time to try and control that.
So the coolant can withstand temperatures of 400 Celsius?
Yeah, so the coolant must this cooling system must be pressurized so the water in it doesn't boil. Yeah. So this is just looking at the overall circuit. You've got the engine, and the hot water that's already cooled the engine comes out, goes through the thermostat to the radiator. It's cooled in the radiator and comes back to the bottom of the engine, and it cools the engine, goes back. And then you've got this other circuit here where hot fluid, hot coolant goes into the heater in the car and back, where you've got a heating system. So the coolant must be compatible with all of those components and be able to transfer the heat from the engine to the radiator, where it's just lost as heat to the environment. And of course, it must lubricate the pump and mustn't cause rusting, must protect all the surfaces against rusting and all that sort of thing. If you look at a typical engine, about 30% of the power is used to drive the vehicle. This would be a diesel engine. Petrol engine would be about 25%. depending on how you're driving, can be as low as 10% in a petrol engine. About 33% going out the exhaust, and the rest is going through the cooling system. So the cooling system has got so much heat coming to it from the engine and has to dissipate that heat to the environment very efficiently, quickly. Water is the best heat transfer fluid. Specific heat of water is by far the best, but it doesn't meet the needs because it freezes at 0 and it boils at 100 and corrosive. So you need something to add to water, that's your coolant additive, that will not, then the water doesn't freeze at 0, it doesn't boil at 100, and it's no longer corrosive. It doesn't cause rust. So that's what we call antifreeze. It's just a coolant additive. That's the major functions. Prevent rusting, prevent freezing, prevent boiling, or lower the freezing point, raise the boiling point. But South Africa, the major function is raise the boiling point. Freezing is not so important. Corrosion, rusting.
So, I mean, that's probably the biggest misconception in the South African market, because when you call it antifreeze, nothing freezes here. We don't need it.
Yeah. But that's why we need it. And if you look at MEG, your glycol, ethylene glycol, is the most commonly used base for your coolant. The propyl glycol is closer specific gravity to water, but specific heat, you can see they're both similar. Water has got a much better specificity than either of those. Okay, so the specific heat for to put so much energy into the, you see, specific heat is calories per gram per degree Celsius. So it will take away more calories per gram. Water will take 4 calories per gram, and your glycol's only 2 calories per gram.
Okay.
So 1 gram of water going past will take 4 calories away. The glycol, 1 gram, will only take 2 calories away.
And what does that mean practically then in terms of coolant?
So it means that the water is a much more efficient heat transfer medium than glycol. So if you're putting glycol in the system, you need a slightly bigger system. That's all it means. But glycol gives you all the other properties. You can see the difference in boiling points, viscosity, the boiling point, and with pure water will freezes at 0. Pure glycols -11, -60, 50%. So the coolant to be used as a coolant, it must have a corrosion inhibitor package in it. It's not just water and glycol. You've got to have a corrosion inhibitor package in it. It's got to be a lubricant for the pump seals and the pump itself. In heavy-duty diesels, an additive to prevent damage caused by cavitation of a liner is also needed. In a diesel engine, you've got the liners, it's a tube, and a piston going up and down inside. On the outside, there is some attraction to the piston going up and down inside to water. And also on combustion, the outside will expand very quickly on combustion because of the pressure inside. And so as it expands like that, the water that's up against it suddenly gets displaced, and you can form bubbles in the water, and then the bubble implodes and starts pitting the liner from the outside. So you need an additive to prevent that.
So you need a special type of coolant essentially for heavy duty.
Yeah. Basic functions of any coolant are to remove excess heat from the engine, to protect the engine from corrosion, protect the engine from freeze damage in cold weather, and prevent cavitation in diesel engines. Well, any engine really. Freezing protection, you can see here, freezing point of water, an antifreeze mixture, pure water, 0 on the bottom here. It freezes at 0. Maximum protection is about 65% antifreeze. You will go down to -50. We don't need -50 in South Africa. So we usually run about 40%, which give us -25. And that is not controlled by what temperature we need to go down to. It's controlled by how much rust inhibitor we need in the system.
So you shouldn't just blindly dilute a 50-50 premix further. You're only thinking about temperature. You actually have to think about corrosion more.
Yeah, you have to think more about corrosion, always. Yeah.
So don't dilute. 50-50 is fine.
Yeah. 60-40 is considered.
60 water, 40 coolant.
Yeah. Yeah. And then boiling protection, you can see water boils at 60%, it will raise the boiling point by 10 degrees. 90% it raises it by about 140 degrees. By 40 degrees. So it does raise the boiling point of the coolant. You know, of the water in the cooling system. Okay, rust protection. You all know what a radiator cap looks like. And you take the cap off and you see that rust in there. That's just some of the rust that's happening in the engine that's now being circulated and deposited on the radiator cap. There's a problem in the engine, you've got rust. And so I've included some slides here that I've taken from various failures. This was a radiator hose where they used the wrong antifreeze. I think it was a Japanese-built vehicle, and they used a European-spec'd antifreeze, and the antifreeze was not compatible with the rubber that they used for that hose in Japan, and it softened the hose and it burst.
The Japanese manufacturer would have specified what that antifreeze needs to be.
Yes, yes. And you'll see just now there's a difference between antifreezes coming from different regions. So this is the same hose, some antifreeze spilt on the outside of the hose. How it's reacted with the hose. You can imagine what it's doing inside. That's why it burst. Okay, these are O-rings. Inside the engine, you've got the combustion chamber with a sleeve that the piston's running up and down in. Around the outside, you've got O-rings, big O-rings that seal there. These are breaking up. Again, using the wrong antifreeze in the engine that's not compatible. I did this work for one of the major manufacturers, OEMs. They were having engine failures, and they eventually called me, and I showed them the antifreeze they're using. And they had to go to a genuine antifreeze, you know, their own in-house genuine antifreeze, which they were resisting up till that stage. Yeah, this is just looking through an inspection cover in an engine at rusting inside the engine. See, the outside of the engine's okay, but there was a plug here, and the inside of the engine, you can see the rusting that's taking place.
How do you, oh, you a stupid question, I'll ask it anyway. How do you know this is not, this is rust not caused by improper lubrication, but specifically cooling?
Okay, that part of the engine was only running with coolant. There was no oil there at all. So only coolant was coming in contact there. That's typical liner pitting, where the engine, you've got the piston going up and down inside, and because of the liner bulging like that every time there's combustion, the water on the outside bubbles, forms little bubbles, and implodes and cavitates, and causes that pitting. So you've got to have an additive in the system to prevent that. That is a pinhole in a radiator. That pinhole developed in 2 weeks of operation. That radiator had been in service for 2 weeks. And they had antifreeze in the system, but they'd mixed antifreezes. And the two antifreezes were not compatible with each other. They reacted and formed an acid, and the acid ate through the radiator. And that's off a big high-no truck. Genuine high-no radiator, 2 weeks, holes through it.
So when you switch from one antifreeze to the other,
Flush with water. And turn the heater on to drain antifreeze out of the heater as well, so that and then you flush the whole system. You fill it with water, leave the heater on, start the engine, circulate, drain it, do it again, and then put the new one in. Cylinder head gaskets. There can be a coating, silicone, PTFE, and where the water now is sealed against the cylinder head to stop it from going into, you know, the water is coming round, and there's a seal there to stop the water from going into the combustion chamber. And that some antifreezes will react with the silicone or PTFE coating on here and start leaking, and then you get leakage. You can see here it's on the cylinder head gasket, it's leaked, it's reacted, taken away the thickness, and then it starts leaking. Here it was leaking, and then you have water coming in. You can see the carbon deposits there, and here they're getting washed off by the water while the engine is running. And that's just because using the wrong antifreeze in that engine. Head gaskets cause all sorts of problems: engine overheating, loss of ring tension, you know, bearing failures. This is bearings from that engine with the water damage on the bearings. Water damage on a big mining engine. Okay, rust deposits in the system. And you can see the rust blocking up the radiator here. Okay, the critical coolant properties: it must not cavitate or prevent cavitation, prevent corrosion on all the different metals you've got in the system. aluminium, cast iron, steel, copper, etc. And must be compatible with all the plastics and elastomers, hoses, O-rings, seals, all that sort of thing. Now, here, antifreeze technology in Japan, they typically use organic salts and phosphates. Silicates are banned. The phosphates and silicates are the rust type of rust inhibitor additives that they put into the antifreeze, you know, to stop the rust from happening. They've got rust inhibitors in them. So silicates are banned because they react with seal materials and engines. You can see that pipe that burst. Europe uses organic acids and silicates. Phosphates react with hard water to form scale deposits, so they do not use phosphates as corrosion inhibitors in Europe because of the hard water. So immediately you can see there's an incompatibility using the Japanese engines will use the pipes that are compatible with phosphates and organic salts. Europeans will use pipes and hoses that are compatible with silicates and organic acids. And so you get that incompatibility between the basic engine components from a Japanese vehicle using a European antifreeze, or a European vehicle using a Japanese antifreeze. Yeah. And then globally, there's oats technology, which uses organic acids and no phosphates or silicates. These antifreezes last significantly longer, more than twice the lifespan of the other antifreezes.
So old technology can work for both Japan and Europe also?
No. The old technology is what we're looking at with Japan and Europe, really.
But
no, sorry, yes.
But Japan, so Japan doesn't want silicate, also doesn't have it.
Yeah.
Right? Europe. But Japan uses salts.
Yeah.
So oats can be used in European cars, but not in Japanese.
Oats doesn't have phosphates or silicates, so oats can be used in Japan and Europe.
They asked. So it can be used.
Yeah.
Oats can be used.
Oats is the global saver. Yeah.
But oats uses organic acids, whereas Japanese use organic salts.
That doesn't. It's just the difference in technology. Yeah. No, it's not an issue.
Oats is universal.
Oats is universal. Yeah. Yeah. And it's just a photo that one, the radiator. I found that place where the radiator came from. These were the antifreezes that they were using. Different colors. Okay, now there are three basic lubricant coolant technologies. There's the CAT, or common antifreeze technology. Traditionally, it's green in color. It's dyed green, and it has a lifespan of about 2 years. It won't last longer than 2 years. Then there's the oats technology, and it comes in many different colors. And that will last 5 years, no problem. So it costs a bit more, but it will stay in service for 5 years. And then the hybrid oats, which is a mixture of both of these technologies, so it won't give you the life of oats. It won't give you 5 years. It'll be 3 to 4 year life.
Tweaks to just make it cheaper there.
To make it a bit cheaper, yes. And yeah, that. Okay.
Can you use oats in heavy duty diesel?
Yeah. Yeah. We'll look at that just now. The conventional additive technology is in organic additives such as phosphates, borates, amines, silicates, etc. They're robust. They've been around for a long time, but they've got a maximum lifespan of 2 years. And they're compatible with most parts of the engine. So that's your typical green one. The oats, fully neutralized organic carboxylic acid, such as been generally biodegradable, very slow to deplete, giving longer life, less reactive with hard water, leading to less scale buildup in the engine, better heat transfer, there's no additive depletion, nitrate, phosphate-free, better cavitation protection for your heavy-duty diesels, and better heat transfer. So oats are the Rolls-Royce. And then the hybrid is a mixed system of organic acids and inorganic additives, longer life than the CAT products, suitable for a wide range of cooling systems. They're pretty robust. And doesn't have the toxicity and environmental issues with CAT products. Just be very aware that the glycols that are used in antifreezers are toxic, they're lethal to humans. If the OEM, only warranty. If the OEM hasn't heard of oats, and he will kill your warranty if you put oats in there, then you have to stay with his recommendation. Okay, this is just looking the relative life between different components. Your nitrites, silicates die quite quickly, very quickly, 20,000 kilometers. They're pretty useless. Your oats technology up at the top there retain 100% efficiency for thousands of kilometers. The other thing that I didn't stress is Europe typically has hard water. So the antifreezes for European conditions are based on hard water, what drives the big difference between the European and Japanese coolant systems.
You should just do oats.
Yeah. And then this is just looking at America up to 2001, 2002 was the old green technology. And then they went to the hat and more of the oats. You can see European were already on the hybrid technology, the yellow, and went to oats. Asia was technology as well. So you can see very different, just the colors, very different technologies in the different places.
The 40 actually means that it can be mixed to minus 40 Celsius. That's the language.
Okay, I thought it was mixed to with 40%.
It's 50-50.
50-50.
But it's minus 40.
Minus 40. Okay. And then the conventional with a 2-year life is the Gazpromneft Antifreeze BS. Choosing between the G Energy HD and the Gazpromneft 12, I don't know.
Well, HD kind of states it for heavy duty. That's why we sell HD to mining and
Okay.
to everybody else.
Because HD, you know, all it gives, it's approved by Cummins and Caterpillar and Detroit Freightliner, etc. Freightliner, for instance, you can buy with, Freightliner makes trucks. They do not make engines. You can specify a Caterpillar, Cummins, or Detroit diesel engine in a Freightliner. Caterpillar, Cummins, and Detroit diesel engines all have their own antifreezes, and they're incompatible with each other. And Freightliner in South Africa had a huge problem with mixed fleets of trucks. All Freightliners, but mixed engines, where they were losing radiators, getting those pinholes in the radiators because they were using mixtures of antifreezes. They would get the Caterpillar engine with Caterpillar antifreeze and then start topping up with Cummins antifreeze, and it wrecked the radiators.
Neil is pointing something out. HD40 data sheet says it is oat, but that it also contains nitrites and the molecules. Is this compatible with oat?
It is oats technology. Nitrites are generally, that's typically used as additive to prevent cavitation, you know, the liner pitting. So that would be good for these heavy engines, the HD.
But the question whether it's compatible with those remains to be asked to Gazpromneft.
I would say it is, by and large, but Gazpromneft would have to show that it's their two products. Are they compatible?
And then lastly, so Neil summarizes for us. So essentially, we can cover all needs of private vehicles with SF12 Plus as a premium product, and all heavy-duty engine needs with G-Energy HD.
Yeah, yeah. There is one other product that G-Energy SNF.
Yeah.
That's oats, and it actually looks, it's free from nitrates, amines, phosphates, silicates, borates, and it meets all, that looks like probably the best product to use.
Okay, and SI oat, G-Energy SI oat. Made is extra long life coolant made out of ethylene glycol. Uses hybrid. Uses oat. Also free of nitrates, amines, phosphates.
Yeah, that would be for passenger car. More, but meets all the Mercedes, Cummins. Mind you, Cummins have got, it's more for passenger car. Cummins have got 27 different antifreezes.
Only, yeah?
Only. And many of those are incompatible with each other. They will cause engine failure if you mix them.